Hi all. So let's talk about a rapid-fire set of unspoken performance optimizations. So LabVIEW is a compiled language. It's fast, but how can we get the most out of it? And so that's how this presentation got started. But before we jump into that, let's have a look at this. This landed into my inbox a couple of months ago, and it hurt me in my soul. It was quite an evening, so of course I couldn't sleep and actually start replying to it and start thinking, okay, clearly there is a mismatch between how people are experiencing LabVIEW and what LabVIEW is actually capable of. And that's how this presentation got started. So let's have a look at what else it can be. So this is a real-world example in which I'm involved, a project with Qblocks and IMAC. It's a single molecule sensing and analysis application. We're sensing molecules, DNA, proteins, and we're actually checking, okay, what do they look like? What's the distribution in a solution, blood, whatever? And to call it high performance might be a little bit of an understatement. So the instrumentation is done in LabVIEW, and it has a somewhat high channel count, between 1 and 10,000 channels. But the crutch is, it's also a high sample rate, between 10 and 50 megasamples per second. That's quite challenging, right? So we're talking data rates between several hundred megabytes per second to even terabytes per second, which need to be analyzed. The reason for that is, well, we need to do that analysis inline, and then actually for a good reason. Two things. First of all, we want data reduction. Saving terabytes per second, well, hard disk sellers will definitely love you for purchasing an entire server farm worth of data, hard disks. It's not really useful. So we're going to reduce the data. We're going to search for actual data coming in instead of saving everything. But also, and more importantly, we want just-in-time results. Our test engineers, they want to run their test and immediately see if their test is going well. Not just, okay, let's call our codes, and then we're doing post-processing over the weekend, over the next couple of weeks, and maybe you will learn that your test failed and something happened to the test and you have to redo it all over again. If you see it just in time, well, what does that mean? Okay, great, something went wrong, let me just quickly adjust it. You lose a couple of minutes rather than hours, days, or even weeks. Now, clearly, this is a high-performance compute setup. So what does the high-performance compute landscape look like within test and measurement, within LabVIEW? So the landscape is, in general, three main components: the GPU, the CPU, and the FPGA. The FPGA is being served by the NI LabVIEW FPGA toolkit. I think by now everyone has heard about it. It's great because it has low latency, which means immediate results whenever there's a stimulus. And it has great support for high-speed communication. We're talking gigabit, it's Ethernet, 100 gigabit Ethernet, Aurora, and of course parallel throughput, where we can do element-wise parallel analysis of dozens, hundreds, thousands of channels all at the same time. And this is, for example, what that looks like. So here we have hundreds, or in this case, 100 channels being analyzed as they come in, searching for features, and every white dot is a feature which is of interest for further analysis. Next up, we have the GPU. This is being served by my toolkit, G2 CPU. And the GPU is great, first of all, for parallel throughput. We can analyze a lot of signals at the same time, batch-wise, so we can work on larger sets of data all at once. And we can process multiple gigasamples per second, which is great. But also we have floating points. There is a benefit to using floating point when working with high accuracy applications where we need to do approximations, stuff like that. And even advanced arithmetic, which might be challenging to implement on the FPGA. As a quick example on how that looks, this is an example of the toolkit where we're streaming from a VST at the full 1 gigahertz on a PXI and doing a 16 million points FFT. Doing a full analysis on the go for hours on end without any issue. This is what the GPU is absolutely great at. And for those of you that are interested in this, we partnered with Radx Technologies for this. They make GPUs for PXIs. Absolutely great products. Then lastly, and that's going to be our main topic of this presentation, is the CPU. It's being served by standard LabVIEW. Well, you're here, so you probably know what LabVIEW does. The CPU, great for floating point analysis, right? We can have double floating points, single floating point. We can quickly do some arithmetic. It isn't challenging at all to do that, while, for example, in FPGA, it might be a little bit challenging. It's great for secondary analysis. A quick calculation here or there just to know how your process is going, and of course, visualization. But the CPU, it has a central role within our computer setup. So that means it has low latency. It is connecting to all different components within the system: network, disk, FPGA, GPU, so it can easily communicate with all of them. So great for connecting the system, and of course, you have that RAM memory, which you can easily expand upon, so that you can also leverage that quite easily. And this is a little sneak peek to what's coming. This is, for example, what you can do with the CPU, streaming data to a TDMS file, or in this case, reading data from a TDMS file at the full speed of the SSD. So that's about 7 gigabytes per second. So that was a little bit the intro. Let's start looking at these optimizations, these CPU optimizations. I tried to put in a lot of different ones, so if something's not applicable to you, maybe another topic is. So we're going to look at data layouts, how we can represent our data, disk I/O, how can we really push our disks to the limit. We're going to look at modern CPUs, how we can leverage those efficiently, and also how can we design our algorithms for this type of high throughput calculations. So first of all, data layout. I want you to consider a single sample, a single measurement, and then the way that we can represent it. If we say we want to represent it as an integer 8, well, it's 1 byte. Now, our computers, they don't care about how many samples per second we're using. Everything is in gigabytes per second, terabytes per second, whatever. So let's transform that. 1 gigasample per gigabyte. Easy, right? Now, if we represent that same sample as an integer 16, suddenly we can only store half the amount of samples in that gigabyte. Still quite clear, but it does mean that with the same amount of memory, we can store less samples in it. It means that with the same throughput our network allows us to do, we can send less samples over the network to a server, which means if you need more, you need to upgrade your infrastructure. And then if you go to single floating point or integer 32, it halves even further, and it halves even further. Now, okay, this is all great, this is all theoretical, but what does that actually mean? Well, let's have a look at, for example, operations. So here I have a little piece of code. So here we're just generating a little bit of data. And then here it's just an event structure where it goes, okay, do we want to do a calculation in I32, I8, I16, 64 bits? And it's all going to do the same calculation, a simple increment. In theory, this should be somewhat similar, right? For each one of them, well, think again. There's a dramatic impact based on the data type we actually use. In integer 8, we can do this analysis at about 13.7 gigasamples per second. If we go to integer 16, it's perfectly halves, 6.45 gigasamples a second, floating point 32, 3.62, floating point 64, or double floating points, it goes to 1.74. That's quite drastic. If you need high performance, if you have a lot of data coming in and suddenly your system is stuttering, this can be quite an impact. This might be the difference between buying an extremely expensive high throughput system or running it on a single board RIA. Now, let's have a look at visualization. So visualization has, I don't want to call it the same issue, but it has the same impact. So here we have a similar code where We're creating some random data, and we're just feeding it into a chart. And in this case, we're not dynamically changing the data type. It's been done during development time. But we're getting similar results. If we're showing data at double floating point, we can get about 2 gigasamples a second. That's on this laptop. But if we go to integer 8, we can go to 36.8 gigasamples a second. What does this mean practically? Well, often, if you need floating point, it might be actually beneficial to just say, well, I'm going to represent it as a single floating point and get that performance boost because maybe I don't need that accuracy in visualization. So by just changing that data type, suddenly we're freeing resources on our system, which might be better used somewhere else. Now for data storage, I want to do something a little bit different. I want you to consider a customer setup. We have an airplane jet engine, about 10,000 RPM. We have 100 accelerometers all over the place. We're trying to measure what is happening, how it's performing. We're doing about 300 kilosamples a second per sensor for a total of about 30 megasamples a second. And we have a 16-bit ADC, quite important. That's our resolution. That's the accuracy of our system. And we're going to test for about 10 hours. That's about 1 terasamples worth of data. That's a lot of data. Now, if we want to store this, depending on the data type, we get a similar drastic change. I think most of us here will just say, okay, we're going to save it as a double floating point. That's the default value. Let's use that. But the impact can be quite drastically different. If we save it as the value as the ADC puts out, it's 2 terabytes, but more importantly, we're streaming at about 60 megabytes per second to the disk. If we have the requirement, it needs to go over the network to a server. What does that mean? Well, we can run this over a gigabit Ethernet. Nowadays, it's in every corporate environment, so it means absolutely no infrastructure change. We can just use it as is. If we go to single floating point or double floating point, we're getting into the gigabit Ethernet range, or above that. So we would need a 2.5 gigabit connection, or a 5 gigabit connection, or even 10 gigabit connection. So that suddenly means often, okay, we need to upgrade the infrastructure, all that good stuff, to just represent the same data that we could have actually jammed through a gigabit Ethernet connection by just considering the data type. Now, of course, you're going to tell me, well, integer 16 is great, but when I open the TDMS file, I don't want to read standard ADC values, right? No, I want to see, okay, how does it scale? What's the unit, Celsius, acceleration, and so on. So in this case, LabVIEW has some great feature. Scaling, the TDMS creates scaling information. This VI, I noticed either people know it exists and use it, or they've never heard about it. They saw the icon and go, I'll check it out later, maybe somewhere next month, next year, next decade. But it's a really useful VI. It allows us to add scaling information to a channel, and we can then say, hey, this is how you go from an ADC value, an integer value, to something useful. And as you can see here on the left-hand side, it's a polymorphic VI. We can say, hey, this is a relationship between a value and the actual representation. It can be linear, it can be polynomial, so we can add coefficients. It can be thermocoupled, RTD. We can create a lookup table to do this. Strain, thermistor, reciprocal. And this is the way that we can ensure that we can stick to, well, let's save the ADC data and let's do the scaling when we actually need the scaling rather than at storage. This is the impact of data layout. By just carefully considering what the data type is, we can drastically improve the performance of our system, the throughput of our system, and reduce file sizes by just keeping that in mind. So that was data layout, but what about disk I/O? How can we leverage modern disks? Well, disks have gone through quite an evolution. Back in the day, SATA 2, SATA 3, they started at about 100, 250 megabytes per second. It went up to 600 megabytes per second. Nowadays, PCIe Gen 4, Gen 5, it started at 5 gigabytes per second and it went way up. How would we leverage that? Well, Most people, sorry, lost my train of thought. So before we continue, first of all, let's consider this system. This is where the benchmarks that we're going to see have been taken on. This system, that's a 990 Pro, PCIe Gen 4. It has an advertised read speed of 7.5 gigabytes per second and an advertised write speed of 7 gigabytes per second. That sounds high performance. It's what the manufacturer claims, but whenever do we trust the manufacturer, right? So there are these online tools, industrial standard tools like Crystal Disk Benchmark, where we can actually see what is the actual throughput my system is capable of. And as you can see here on top, 6.8 reads, or 6.8 gigabytes per second reads, 6.7 gigabytes per second writes. This is what we paid for. This is what we want to see from our system, because when we are speccing a system, this is what we're looking at. Now, with the regular TDMS read-writes, you would have something like this, something similar. Of course, it's a bit simplified. We open it, we do the read-write action for as long as needed, and once we're done, we close it. This works great up to a point. On the system where I was tweaking the package sizes, really trying to figure out, okay, how can I optimize this absolutely for throughput? I got up to about 2.7 gigabytes per second and a read speed of 2 gigabytes per second. Going back to our benchmark, our synthetic benchmark, this is what we paid for, and this is what we got. And then, of course, I can understand the claim where people go, well, performance is not... No. Let's see how we can do it better. So to understand how we can do it better, let's have a look at the problem. Reading and processing of the data, going from disk into the RAM memory and making it available to LabVIEW, it's happening sequentially. So first of all, this is extremely simplified. I know it's more complex, but just for the sake of this presentation. If you look over time, we have a reading action where data is being transported over the disk to the RAM memory. And then there's a bit of processing happening before it's available in LabVIEW. And then once it's available in LabVIEW, we do the next iteration and we do another read. Every time we're doing processing, the disk is sitting idle. That's useless, right? Well, another problem here is this disk read and processing time, it scales with the amount of data we're reading or writing. So if it's 100 megabytes or 200 megabytes, the time is about the same, or the scaling is about the same, so 2 times. Again, simplified. Now, I've learned a long time ago, to give a problem without a solution is just complaining, so let's jump to the solution. Well, first of all, we have multi-thread systems, so why don't we just process it across multiple CPU cores? And while the first one is processing, start reading the next one. So we process a chunk, read the next, and this is what that would look like. Disk reads, we process it, and while we're processing it, to the next disk read, and the next. Suddenly, our disk is constantly in use. Now, when we want to code something like this, it might seem super complex, but actually, National Instruments has us covered here. If you go to the file palette, lost track here, there we go. Buried way deep into the file I/O, TDMS streaming, advanced TDMS, TDMS advanced asynchronous I/O, and I think at this point they just ran out of letters they were allowed to use. There is an entire function set that does all of this. So instead of us needing to design a complex framework, architecture, algorithm that does this for us, LabVIEW made it simple for us. So in this case, the asynchronous TDMS read-writes, well, first of all, we do an advanced open. Please keep in mind this is different than the regular TDMS open. We're doing a configuration. We're telling it, hey, how many threads do we want to use at the same time? How much are we going to read at the same time? And then once that's done, we're going to tell it, okay, start your threads, start reading, and it's going to happen in parallel while our while loop here is constantly reading. With reading, I mean whenever a thread is ready, it has data available, it will send it to the asynchronous reads, and we can send it over with a queue to another thread to do further analysis, and it's the same for writing. And then once we're done, we close it. With 2 extra VIs, we drastically improve performance. Write speed, 6.46 gigabytes per second, again, on this system, on this laptop, and a read speed of 7.12 gigabytes per second. Now, I want you to quickly consider back to the synthetic benchmark. This is what we paid for, and now we got it. And actually, great job, Anna. You made codes which we can use, which is better than a synthetic benchmark. So, yeah, absolutely great stuff. But, and there's always a but, I had this professor at university, and he said, well, there are a couple of laws in nature which are unwritten, and one of them he called the preservation of misery. First of all, modern systems, these SSDs, they're becoming smaller. And suddenly we need to start considering temperature. As you can see here, we are reading at 6.5, or between 7 and 6.5 gigabytes per second during this run. Probably chunks were not that great. And suddenly we see a dramatic drop to about 3.2, 3.3 gigabytes per second. Not only that, if we go into the statistics of, or the information on the drive, we can see there is a warning. And you can also clearly see drive temperature going to 92 degrees Celsius. This is the drive protecting itself. That's the first problem, something we need to consider. It can be quite a big issue because you're expecting 7 gigabytes per second. Your customer is expecting 7 gigabytes per second, and suddenly it drops to 3.2, 3.3. Also, something that we need to consider is the write cache. So SSDs are actually tricking us. When we're writing, and they're advertising 7 gigabytes per second, well, they can only do that for so long. There's something called a write cache, a couple of hundred gigabytes often, which can write at that speed. But after that, we can only write at the speed the SSD is actually capable of, the large memory is capable of. Usually it's about 10% of the disk size, which is fast, and then it drops down, and then it needs to move all the data over before it can go that fast again. So again, you would see a drop like this to 1.5. So when we're speccing a system, we actually need to look at more than the flashy marketing notes. If you dive into the specifications, we're going to see, oh, this drive has a specific write cache and a cache exhaustion speed. So once we go past that write cache, this is the speed we can only get. And then what we need to do is, okay, we need to stop writing, let it slowly move everything to that slower memory so that fast memory is available again so we can stream data. Again, I'm giving a problem without a solution. It's just complaining. So let's talk solutions. Write cache limitations. Well, the easy solution is using a RAID array. Instead of writing at the full speed of each disk, for example, 8 gigabytes per second, we can write to 8 disks at 1 gigabyte per second. If we're below that cache speed, or that cache exhaustion speed, it never drops its performance. This is a solution for PCIe. Radix Technologies also makes RAID solutions for PXIs. Everything from in-slot to even external ones that hook into the PXI, which go up to a petabyte. So you can write for an extremely long time. Now, that's cache, but what about temperature? Well, it really depends on your setup. You can add better cooling. Some SSDs come with their own heatsink. You can add aftermarket. You can go way overboard if you want. And some setups also have integrated cooling for disks. That's one solution. Another solution is RAID. If we're writing, 1 gigabyte per second to an individual disk, but in total 8 gigabytes, well, that 1 gigabyte is going to stress the disk a lot less. So it's going to overheat a lot less. Again, allowing us to reach the performance we need. Next up, CPU. So the last couple of years, there has been a little bit of a chatter. The regular dual-core, multi-core is a little bit dead. Nowadays, it's become more complex with big, little architecture. So some of you might have already noticed, CPUs, you have performance cores and efficiency cores. These big P cores, performance cores, they take up a lot of space on the silicon, but they do provide more performance with the cost of more power, meaning more heat. And you will find a larger distribution of these P cores in more high-end machines, high-end CPUs. If we go to efficiency cores, these little CPUs, as the name might suggest, it takes up less space, has less performance, less power usage, so less heat, and you will often find these in laptops and lower-end machines, or a larger distribution of these. And this can cause issues. Again, problem. If a customer comes and says, well, we bought the same system, a 16-core, 3 gigahertz, but suddenly we're not meeting specifications, and then you go, oh, well, procurement, they actually chose the cheaper CPU with more efficiency cores than performance cores, and suddenly the system is stuttering. The Windows scheduler is aware of these performance cores and efficiency cores, so you might get into a situation where you have a lot of high throughput loops, and suddenly Windows is saying, oh no, this needs to be in the performance, this needs to be in performance, suddenly it drops to efficiency. Your loops start competing with each other, and Windows doesn't really know, okay, how do I prioritize that in a constructive way? And of course, that also means a lot of context switching. Suddenly you're seeing jitter, timing's not being met for a fraction of a second, and suddenly everything's going okay. It's a mess. Now, again, LabVIEW has the solution. Timed loops. Timed loops, they allow us to take control of the threads themselves. We can say, okay, just run at the full speed, so cycle time of 0 milliseconds, so it acts similar to a regular while loop. But here, we can define which CPU core to run on. And this actually works directly with that big little architecture, because that index is directly related to if it's a big or a little CPU core. So for that, I made this piece of code. Sorry, it's a little bit small. So on the top, we're checking how many CPU cores do we have available. That feeds into this for loop. We are generating some random data here. We feed it into a timed loop where the CPU selector or processor ID or process ID is linked to the iterator. And we're doing some big FFTs, which take up a lot of time, a lot of processing, and then we're getting the median time, which we're going to put in a graph. So when I run this code, you're going to see something like this in your process manager. You're going to see this spike migrating from one CPU core to the next. We're profiling each CPU core. And at the end, we get a graph like this. As you can see here, the time, which is the y-axis, and the x-axis is the processor ID. We can see at the beginning, it's about 9.5 milliseconds, quite fast. But suddenly, it jumps up to about 15 milliseconds. So we lost 50% of our performance by just switching between those CPU cores. Now, again, that's quite dramatic, but this is a great way that we can profile it and also select, okay, this is code that we want on the efficiency core, or this is code that we want on the performance core. But what code would you put where? This is a little bit my personal helper, where I go, okay, what needs to go where whenever it becomes an issue? I tend to recommend, well, first of all, the P course in your DQMH, in your actor framework, you want to let your helper loops go on the performance course, especially if they do a lot of high throughput analysis. Also, device communication, communicating with high throughput devices, which send out a lot of data acquisition, DECMX in and out. That's normally what you want on a P core. The little E cores, they're great for example, the UI, where, okay, if the UI stutters a little bit, it's not as bad than if your loops, your feedback loops start stuttering. Then suddenly you get real issues. Also, I tend to recommend the actor or DQMH course, which normally just pass on messages. They shouldn't do that much processing. Often are well suited for those efficiency cores. Same if you have a state machine, which just monitors a system. It doesn't really do that much. It's often better to make sure it's on an efficiency core, so those performance cores are available for the actual high throughput part of our application. Now, lastly, we're getting to the algorithms. So we went through the hardware, but we can also change the way we design our algorithms, our pipelines, to facilitate high throughput. Now, for this, I stole an idea from security. It's called the Swiss cheese model. The idea is you have multiple slices of cheese, and you're never going to be able to fill all the holes. But if we add multiple slices of cheese, one after the other, eventually there's no hole that overlaps. And we can use something similar here, where instead of having one big algorithm, which does all the work, which is extremely expensive, it needs a lot of processing, we can say, hey, we're going to add really efficient algorithms on the beginning to weed out 99% of the data that we don't need, and that 1% can go on to more complex, more expensive calculations. So instead of trying to do everything with one algorithm, we can be smart about it and just layer it up. So using simple algorithms to do initial reduction of data, only saving the parts that we're truly interested in for the more complex algorithms. I tend to recommend ON notation, so that scales linearly or even better with the amount of data. And I tend to recommend that these algorithms scale to an FPGA, GPU, and CPU. If you use algorithms which are portable in this way, if suddenly you need more performance, you might need to redeploy your algorithm, but your test data is valid, your testing was valid, and it can easily transport to another more higher performance hardware. And then as we go, we can use more complex algorithms, more expensive algorithms to further reduce the data. Now, what does that look like? Oh, sorry, simple fast algorithms, complex slow algorithms. Now, what does that look like? Well, let's talk about simple feature detection algorithms. You might actually already use them. For example, in DECMX, you have triggering. This is actually one of the ways that we can already reduce the data. Instead of streaming the entire thing through, we're only triggering, and when something happens, we're sending in that data. Now, that's not always a possibility. Sometimes the data is a bit more complex, a bit different in nature. It needs different types of filtering, depending on what action you're doing. So how would you cope with that? These are a couple of my favorite algorithms that I like to use. One of them is what I call the windowed min-max. In here, you have a hyper-realistic signal that I've drawn really quickly in PowerPoint. So here you can see there's this little peak, and then here there's this little valley. These are features of interest. This noise floor, it doesn't really interest me. It's constantly happening, but whenever there's a blip, that's what I want to use. So the windowed min-max, well, it's in the name. We window it. We say, hey, let's grab certain windows. We're grabbing the min-max value for each of those windows. These are extremely efficient operations. We calculate the delta, and as you can see here on the left-hand side, the delta is quite small between min and max. If you look at the middle, delta is quite big, so there is something of interest here. We don't know the nature, we don't know if it's a positive peak or a falling peak, we don't know what the shape is, But we don't care, because if these peaks only happen every so often, we already weeded out 90%, 99% of the data. So we check the delta. If it's across a certain threshold, we know, oh, okay, there's something of interest here. The cool thing about an algorithm like this is it scales to both the FPGA, GPU, and CPU. All of these can deal with it in a really efficient way. Now let's talk about another algorithm, the windowed average. I think by now you're seeing a trend. Take a window, grab the average for each of that window. And through this, we can see if there is a state change, if there is a level shift, by just looking at the deltas in between. At what point did our system change states? We can grab those windows and we can send those on for further processing. Again, something like this is extremely cheap to implement on the FPGA, GPU, and CPU. For example, the FPGA, it's just adding the values until you're at the end of the window and doing your bit shifts. Couldn't make it much cheaper than that. Simple addition, that's all that's happening in a little counter to see when you're at the end of the window. Another one that I like to use is IIR. Now, there's often a discussion, should I use IIR filters or FIR filters? And it really depends, but not in the way that you think. The IIR is an extremely cheap filter. It doesn't use a lot of calculations. The FIR, on the other hand, does. But why would you want to use the FIR compared to the IIR? Well, the IIR, it's more efficient, but it's less accurate, especially in the phase domain. It causes issues. The FIR is quite accurate. So, for example, we can use an IIR to say, hey, is something happening in the frequency domain? With just a couple of calculations, we can then see, oh, there's something of interest here, let's use it, or let's not use it. Lastly, one that I also personally quite like is the leaky integral. So I stole this from electronics. When you're working with op-amps and you have an integral circuit, often you want to make it leaky so it doesn't go into infinity. We can do something here. Here, we're constantly taking the sum, and as if there's some peak, you can see the sum constantly increasing. But it would just go to infinity, and that's not really useful. So what we can then do is say, hey, over time, let it gradually go back to the original signal. This is useful, for example, to measure the amount of energy in a certain feature. If there was a quick blip, our min-max would trigger. But for example, the leaky integral would say, well, that it was a flash in the pan, it just quickly happened, and now it's gone. For example, on the left-hand side, so your value is not that high. But if you go all the way on the right-hand side, this feature with a lot more weight to it, a lot more stuff is happening. You can see that peak increases. That might be something of interest. Again, these algorithms, they translate extremely well to the FPGA, GPU, and LabVIEW. Now let's talk really quick about complex algorithms. I'm going to power through these quite quickly because you probably already use them. So complex algorithms can be advanced state machines rolling over the data, seeing, hey, was there a peak, then a valley, then this feature, then that feature. Quite complex, quite expensive. But if we've already removed 99% of the data, we can afford something like this. FFTs can be quite expensive. AI and machine learning. If you have terabytes per second going into a system, no GPU can deal with that amount of data. You would need to have dozens, if not hundreds of GPUs to do that machine learning. If we can already reduce the data, suddenly it becomes manageable for a single system. And lastly, something like wavelet transforms is also useful. Using a strategy like this, it allows us to use something with the power of a single board Rio rather than a supercomputer. By the way, this is my favorite supercomputer just because it has built-in seating. Just please bring that back. So this is quite powerful. So during this presentation, we had a look at the different types of optimizations we can do. I hope some of them are of use to you. So this is why they were rapid fire. They went all over the place. So if there's something of interest, you can definitely use it. And of course, the role of the CPU in the high-performance compute landscape. It's not because the CPU has less performance than the GPU or the FPGA. That's not relevant. If you're interested in GPU computing, you can always go to g2cpu.com and see how you can do GPU computing in LabVIEW. If you're interested in consultancy for high-performance compute projects or anything else, you can visit qplox.com. If you want to contact me personally, you can contact me at nathan.biesmans@g2cpu.com. And all that's left to say is, thank you.
Thank you. It's an extremely interesting lecture. I have a lot of questions, but one I ask now. So I tried, a couple of years ago, I tried to improve performance of mathematical calculations, moving from double to singles. And I got increase of calculation time. My feeling, so that many built-in functions internally convert everything to double. I didn't investigate. I had no resources to do investigation. I rolled back to doubles. Your comments, if it is true, and if it is true, how can we identify which functions must be rewritten to single to get better performance? Finding bottlenecks.
So the best way to do it is just benchmark it. I also encountered a lot of the signal processing calculations within LabVIEW are just doubles underneath. And that does cause some issues. And it happens from time to time where I just get to a position where either I need to transport it to the GPU, but maybe I need that low latency as well. So then I need to consider rewriting a certain function in LabVIEW to support single floating points. I've done that for quite some, for example, waveform functions. The waveform data type supports single floating point or even integers. But when you feed it in a lot of these waveform functions, they automatically cast it back to double floating points, causing quite some issues. Does that answer your question? Wonderful.
So along those lines, actually, I think that's this big question mark. I do a lot of signal processing as well. I've run into that exact problem of like, oh, where's our single precision FFT? And I know that we have one because we use it underneath in our RFMX software for doing things. And there's a variety of other ones that maybe lie underneath other things that we haven't made fully fledged or out there. But there's usually this, well, how many people really are going to benefit from that? So, well, obviously for one, but I guess for a show of hands to the LabVIEW folk over there, how many people really would love to have a lot more single point precision and it would impact your work? So, okay. Me too. There you go. I'm going to raise my hand too. Right? 2 hands. Hey, everybody raise both of your hands. There you go. Make it look like it's more. So hopefully, thank you very much.
So thanks, Leighton. I don't know if this is a question you can answer or someone from NI can answer, but obviously the big little architectures are quite new. What you've described makes perfect sense, but requires quite a lot of profiling and control. In theory, Intel and Windows provide some automatic scheduling to try and get this right for you. I've never seen much documentation around how LabVIEW interacts with that. Are there versions of LabVIEW that work better with that than others? Have you seen any documentation, or can anyone from NI point us anywhere to understand that a bit better?
First of all, I can say I haven't seen any documentation on it. I might be wrong, but personally I haven't seen anything. But I just found that time loop does get me a long way. So for example, one of the ways that I implement is, well, I use the priority of the time loop, but I also use the high priority functions tend to get a lower index on the processor ID, while the more lower priority items get a higher index. So that depending on which system they run, I did notice that the lower IDs tend to be performance cores and the higher IDs tend to be efficiency cores. So I try to leverage that to where I can. But There's no rule of thumb, or there's no true written rule, and at this point, I'm not sure if that might change in the future, where it suddenly gets swapped around or becomes random. I have no way of guaranteeing that at this point, but it's a way that I'm currently doing my development. Maybe NI has a...
Yeah. LabVIEW doesn't do anything special to control which cores our threads run on other than the timed loop. So we're just getting whatever Windows does. But if you do set your the execution priority higher within LabVIEW, that is using Windows thread priorities, so that should favor the performance thread cores if that's naturally what Windows does. So that may be a tip on trying to get better scheduling onto those cores.
Excellent.
Quick question on the asynchronous TDMS. Is there a reason why you wouldn't use it?
The main problem that I've seen with it is it's extremely easy to go over the limits of a TDMS file. So each channel, if you want them to keep it indexable, that for example you can read it in diagram, it needs to remain below, I think it's 2 billion samples. If you go above it, there's a little field in the TDMS spec which tells you how many samples are in there, and it's a 32-bit number. You can blast right past that, that's not an issue, it will just flow over. But then suddenly LabVIEW loses a little bit of its training wheels, its guideline, its guides, and you need to take manual control. It's a bit of an issue, so NI, please make that 64-bit, please. But yeah, so that's the only one that I've truly encountered where I would encounter something like that. Maybe another thing that I did encounter was, for example, if you make your chunk sizes that you're writing. First of all, my recommendation is make sure it's power of 2. Perfect to the power of 2, that's most optimally using the hardware. But I did notice if you make a little mistake in that, suddenly it's not readable with standard TDMS read-write unless you make the chunk sizes the same as with which you've written it. So you have to keep that in mind. Cheers.
I think we might have to leave any more questions till the break. Is that okay? Because he's just running over and just trying to keep the schedule. Sorry about that. Thank you, Nathan. Nice one.
Excellent. Cheers.